Hi, this is Ollie Collins, and this is my video demo for homework assignment number 9 that deals with Dijkstra's and Kruskal algorithms. So we'll start with my program for implementation of Dijkstra's algorithm. Here's the class that implements it. The class that's going to represent our edges. So um, the uh, the neighbor this edge points to and its weight. This is just a helper class that's going to store the results of our algorithm when it finishes. So it's going to store the best distances to each vertex from the start, as well as each vertex's previous neighbor uh, along the path that it took to get to this best distance. So here is what we're actually putting into our priority queue. We see it implements the comparable interface, and that's because that allows us to use this compare method. It allows us to take two nodes and compare them, um, essentially by their distance to the start node. Now here is where our actual Dijkstra's algorithm implementation begins. So uh, again, this dist is going to hold um, our best distances to each vertex, or at least our current best guess at the best distance to each vertex. And similarly, prev is going to hold the previous vertex to each node. So as usual, we're going to initialize all the best distances to infinity. In this case, we just do integer.max value. And we just pick the biggest number possible that we can get on a computer. And we make sure they don't have anything in the previous record. Except for that we put for the start vertex, it gets a distance value of 0 because of the start. And then we add the start vertex to our priority queue. And this while loop performs the algorithm. Um, so we're going to pop the first element off the priority queue. If this is step 1, we'll pop the start node off. We'll extract its information. So what's the current node? What's its current distance? Um, this is a check to see if we have any outdated entries in our priority queue. So maybe as we're going along through our graph, checking edges, moving to vertices, a certain node might get entered into our priority queue twice. So this just kind of cleans that up. Of course, if we reach a node that has no outgoing edges, that means we've reached a dead end in the graph. So we'll just continue. And here's the big part of the algorithm. Um, so what we did in the beginning, I don't think I covered this. No, we did. Okay, we're good. So for our current vertex, we're going to get all the edges leading out from it to other vertices. And then we're going to see, hey, is it faster or better to go through U, take this edge, and get to V? Is that better, or is that a shorter distance than what we had in our dist map before? If it is, that means we've just found a better path to V that's going through U. So we update V's dist and put its previous value to U. And then we actually add vertex V into the priority queue to be examined later. But notice we have a for loop here, so we iterate through all the edges leading out of U before we even get back to examining this priority queue. So we just put stuff in the priority queue, iterate through all the edges, and then start back over here. We'll pop off the shortest distance vertex now, and then go through the whole process again. And that is what Dijkstra's algorithm does, and eventually it should work its way throughout our whole graph and find the quickest path to every vertex. Um, Out here, the result, so we get the minimum distances to each vertex. Um, but the only thing we've tracked is their previous vertex along the path that it took to get there, right? So we actually need to be able to reconstruct this path so we can show people results. That's what this reconstruct method, which is aptly named, does. So it starts, you given it our start vertex and then the vertex you're interested in. We start at the end because we have these previous vertices saved. So then I know start at the end, go to this previous vertex, then go to the previous one to that, to that, to that, until we eventually reach the start vertex. The start vertex has a special property that its previous vertex is itself. So that's what this if condition here is checking. If this eventually becomes true, that means we've reached the start vertex. That means we've reconstructed our path. Our path was built backwards, so we reverse it to get kind of the true intuitive order. Um, so this was the code. The project requirements required us to be able to accept file inputs as well. So what this does is it's able to read a file input and convert that to a graph. So we just read through the files. If we look here, the file requirements means that every edge should be represented as such. Its origin vertex, its end vertex, and its weight. So what we do is for each line, this should be, its own line. Next edge be below it. So trim the white space off it. Check if it's empty or starts with a hash mark. And then because we have this white space here, we can actually split on that white space. So we split on that white space, extract the information because now we have its two vertices and its weight, and so we can save those. And then with that information, we can jump back in and start creating our graph. So let's see this algorithm in action. So if I run it, looking at the hospital, we see that the most optimal path from the hospital to the accident is to go from hospital, start at the hospital, take road A, and then you arrive at the accident. The total time it'll take is 5 minutes. Moving over to our Kruskal algorithm implementation. Again, we're going to set up our edges. This one have a lot of parallels to the Dijkstra algorithm implementation, but we'll set up our edges. We implement the comparable interface again so we can compare nodes. Then here we have union find. Well, this contains a bunch of the helper methods that are going to make our algorithm work. So first we have make set. Essentially what this is going to do is it's going to take our initial set of nodes and make each one of them its own set. That's going to kind of initialize our process. Then we have the find. So this recursively just finds the root of a set for a given item. If we go down to union, this method is going to be how if we have two separate sets now, how we can join them together. If their roots are equal, then they're the same set. We don't do anything. Otherwise, we merge them together based on their ranks. The rank is essentially how many items are in each set. So the lower rank item gets merged to the higher one by making its root point to the root of that higher set. Get a helper class to hold our results. And then this is our implementation. It begins. So we take all our edges, we sort them, use make set to initialize it. So we take each vertex, make it its own set. This will hold our edges that will eventually make up our minimum spanning tree. And then we just iterate through the edge list one by one by one. So for each edge, they're stored lowest weight to highest. We'll take its two vertices at the end. we'll calculate what their roots are. If they're in different components, then adding this edge won't create a cycle, right? If they're in different components, that means there's no edges connecting them. So if we add this current edge, uh, we shouldn't make any loops or redundant paths. So we just continue this process until we've iterated through the whole edge list. And by the end, this MST result should hold all the edges representing our minimum spanning tree. Again, this is a method to help us read a file if that's the input we want to work with. Here's a sample application I came up with, and then below is the power grid. So let's run it, see what happens. So we see for the power grid task, the minimal span of tree, it's the edge from station 1 to station 2, and the edge from station 2 to station 3. This first edge has a weight of 3, second one has a weight of 4, so the total weight will be 7. For the example I came up with right here, see that the minimum spanning tree is the edge from A to C, the edge from C to D, and then the edge from A to B. And altogether, if we add up their weights, we should have the minimal weight of 9. So this was my implementation for homework number 9. I'm glad it's not 20 minutes. I mean, it's still 11, but I think I did a lot better. So thank you for listening, and take care.